Good evening to everyone. Welcome you all to the seventh problem solving session for this course titled Principle of Communication Systems. We'll wait for another 2-3 minutes for the audience to join and then we'll begin. Hi, can you please confirm you can hear me, right? Okay, okay. Thanks for the confirmation. Okay, so we have enough audience, so let us begin. So in week 7 we are mainly going to discuss a key concept in digital signal processing, which is also kind of fundamental to our communication systems also, that is uh, Nyquist rate. And the context is kind of important. For example, we have to often move from analog signal to digital signal and vice versa. So the idea basically is whatever we mm, the signals that is in the nature are mostly analog, but it is sometimes quite difficult to do that processing in the analog domain. So we have to take the signal again in our communication context. We can talk about wireless signal. uh, for example, you can transmit for example, you consider the transmitter and receiver, and you cannot really transmit digital signal, you have to transmit analog signal, but once it reaches the receiver, or uh, the signal being transmitted from the transformer, before that the processing mostly happen in digital domain. So let's say this is what I am calling a transmitter and this is a receiver. So when you transmitting this happen in analog domain, you have to transmit analog signal, not a digital one. But often the processing you do before transmission, that is the let's call it pre-processing, or let's say at receiver end the post-processing, basically after receiving the signal. This mainly happen in digital domain because it's much more efficient, simpler and faster. But the key understanding here is basically we have to move back and forth between analog to digital domain. And one of the fundamental thing you need to ensure here, that when we seamlessly move between analog to digital or digital to analog domain, there ideally there should not be any loss of information. So ideally we have to ensure no loss of information. So if you ask me what is the one key term which should ensure that there is no loss of information no matter I move from analog to digital domain, so that is, I would say, it's a Nyquist rate. Of course the detailed discussion will be discussed in this session only, but this is the main idea. So I guess I kind of able to motivate it. The idea is that whatever you transmit over the practical channel, that is analog signal, but the processing happen in digital domain. So in signal processing you have to move between analog to digital and digital to analog multiple times, and in that procedure you have to ensure there should not be loss or loss of information, because of course if I transmit something analog signal, let's say from transmitter to receiver, and it turns out from analog to digital domain I have some information loss, then it's pretty bad, right? So I have to ensure ideally there should not be any loss of information. So we are going to talk in details about how that can be ensured. So here, so you are given a signal here MT, and basically you are supposed to find the minimum sampling rate required for the signal to avoid aliasing. So there are few terms here which maybe you are seeing for the first time here. So one thing is sampling rate, second thing is aliasing. So aliasing, let me call what this is. This is basically a distortion. So based on our previous discussion, I guess we have already understood that we have a signal MT, basically, which is the analog domain, and we have to sample it. And the question here asks basically what is the condition so that there is no distortion. So this no distortion, you can see it is nothing but equivalent of loss of information. So that is what I mean by distortion. So the question is how to ensure that, or to be more specific, what should be the sampling rate. Now to answer this question, we have to understand the uh, when you move from analog to digital domain, what is basically happening, so that we can actually see that when there is going to be distortion and when there is not going to be distortion. So let us write down our signal here, that is 15 sine 5000 sorry 500 pi t over t. This you can already see is kind of a sinc function. The structure we have to just bit of rearrange it. So this 500 pi t, if I compare it with 2 pi fm t, then my message bandwidth comes out to be 250 hertz. Now let me draw the signal, kind of let's say AMT takes a arbitrary structure like this. So this is my signal and I have to pretty much sample it. And what do I mean by sample? Let's say I need to sample MT every ts second. So what do I mean by that? If this is MT, in x-axis we have time, so I am supposed to sample at every ts second. So that means I am basically going to pick the value of MT at every ts. Let's say this is 0. I am just considering it reference. So I am going to pick the sample at ts, 2 ts, 3 ts, like that. Similarly, minus ts, minus 2 ts. Remember, the minus might look a bit odd, but it's just the reference, since you are taking the reference point here. Here minus mean it's before the reference point, that's all. It's advance and delay logic based on the reference point you choose. So basically I am planning to pick these points, right, at an interval of ts second. I am interested in the samples. For example, this sample is m of 3 ts, this sample is m of 2 ts, this one here is m ts, this is m0, this is m of minus ts, this is m of minus 2 ts, like that. So I am interested in the samples. So of course, whenever I say that I am sampling every ts second, that means inherently the sampling frequency concept comes into picture, which is given as fs 1 over ts. Basically fs is the number of samples you pick every second, that's all. Now of course, from the question we realize that there is a relation between the aliasing or the distortion or the loss of information and the sampling rate. So intuitively you can see there must be a particular sampling rate which ensures there is no loss of information, and vice versa, that is for sampling rate below or higher than a certain value, it will cause loss of information. So our goal is to learn the relation here. So let's look at from bit of mathematical point of view. I have the analog signal MT. I want to pick this discrete sample. So how I can do that? I mean, in terms of mathematics, how can I recover these points from MT? So for that you need something called like pulse train. So you need a pulse train. So what are these pulse trains? So these are basically these delta functions at the sampling locations. This is of course ideal pulse trend. Let's say it is 0, then it is Ts, it is 2 Ts, then it is minus Ts, this is minus 2 Ts. So that corresponds to, by the way, ideal pulse trend this here corresponds to ideal sampling. Since it's a delta function, it is basically supposed to pick these elements and discard everything else around it. Of course, in practice it doesn't happen that smoothly, but let's try to build the math first, then we'll go to the practical implementation. So how can I represent this pulse trend mathematically? You can see it's basically sum of all these delta function at different sampling locations, right? So for example, the pulse here, this one is del of t plus 2ts. Why? Because it's minus of minus 2ts, that's why. Here it's del t plus ts plus del t plus del t minus ts, like that. That is the expression for this ideal pulse trend. So if I plan to denote it as GST, it has following structure. N runs from minus infinity to infinity del t minus n ts. It okay. So the ideal sampling process is nothing but multiplication of message signal empty with this impulse trend. These are basically impulses, so I am calling it impulse trend. So this is what would lead to my discrete sample values. So what is the structure then? Message signal is empty times n minus infinity to infinity delta t minus n ts. And what this multiplication is going to do, you can see the impulses at the particular location going to pick the value of message signal at those instant. So we can write it as n minus infinity to infinity m of nts, because the impulse at the location of nts is going to pick the value of message signal at nts. So this becomes its amplitude and this remains same. So this one becomes the time domain representation of sampled signal. Let me introduce a slide here. So what does it represent when I say time domain representation of sampled signal? Visually you can see like this. This amplitude here is m0, this amplitude here is mts, this one m2ts, similarly at other points. So this is your sampled signal. Of course, when I say sampled signal, there should be a mention of sampling period. That is Ts. Now I am interested in the Fourier domain representation or the spectrum of the sampled signal, because it's actually much easier to see what is exactly happening, or the concept of aliasing or the distortion, which I mentioned as loss of information, is something that can be understood quite well in the frequency domain. How? I will come to that. So let us next look at the Fourier domain representation of the sampled signal. So let us move to the time domain representation. What do you see? It's the message signal times impulse train, right? MT times this. So Fourier domain representation, what is going to be? In the time domain, it's multiplication. Let me just remind it MT times GST, right? It's going to be MF, which is the spectrum of message signal. Multiplication in time domain, frequency domain leads to convolution, F of GS. Now we are interested in the frequency domain representation of the impulse train. So we have already seen that this impulse train is kind of a periodic signal, right? This is a periodic signal with period Ts. It's because every Ts time instant it repeats itself. It's simple. So our impulse train GST is periodic with fundamental period Ts. So we have earlier seen that for a periodic signal we have Fourier series representation, and for a periodic signal we have Fourier transform. So GST must have some Fourier series representation since it's a periodic signal. So let us write its Fourier series representation. GST as Cn e to the power j 2 pi n fs t, where fs is inverse of the fundamental period here, 1 over ts. Now we have to find this coefficients Cn. coefficient Cn is 1 over Ts. Integral runs from minus Ts over 2 to Ts over 2 GST e to the power minus j 2 pi n fs t dt. So since there is only one impulse in this particular range, this is going to be this. Now it's same as 1 over Ts e to the power minus j 2 pi n fs t evaluated at t is equal to 0, which just reduces to 1, so Cn comes out to be 1 over Ts. So you can write GST as 1 over Ts n minus infinity to infinity e to the power j 2 pi n fs t. Of course, now if I bring it to frequency domain, what I am going to have, amplitude remains same, but it's a complex sinusoid in time domain. So in frequency domain, it is going to be shifted impulses. So 1 over Ts n runs from minus infinity to infinity del f minus n fs. So this is what we are calling as capital G S F, that is same as this. Or if I plan to write it in terms of Ts only, 1 over Ts n runs from minus infinity to infinity del f minus n over Ts. So remember, just to give you the context, what we are planning to do, we have this analog signal, we are willing to find the minimum sampling rate that will ensure that there is no aliasing or distortion. So how to find that? So first we have analog signal, we know that we are going to sample it at certain period. We find the sampled signal representation in the time domain, which is given by the message signal times the impulse train, considering ideal sampling, which sample signal has this following time domain representation. Next we are interested in finding the frequency domain representation of the sample signal. It's a frequency domain representation. And how? So what we do, we know that in time domain is the multiplication of the impulse train with message signal. So frequency domain is going to be the convolution of the message spectrum with the spectrum of this impulse train. The spectrum of the impulse train comes out to be another impulse train, you can see here. Okay, this is one point I want to emphasize, like we have seen that impulse train is a time domain is the impulse train, and in the frequency domain representation is also an impulse train. So basically the sampled signal frequency domain representation is the convolution of message spectrum with this impulse train in the frequency domain. Let me point it out. Just a minute. So another impulse train in frequency domain. It's a quite interesting property. An impulse train in time domain, its frequency domain representation is another impulse train. So we are going to use this property. So let us introduce another slide. This slide looks a bit clumsy. So our goal is to find the spectrum of sampled signal which we denote as, okay, we have not denoted as anything, let us call it m delta f. So spectrum of a sampled signal m delta f is given as mf convolution with g delta f, and this g delta f we can write as 1 over ts impulse train in frequency domain. Let me write it in the frequency term fs here. Sorry, nfs. So we know what we get when you convolve Dirac delta impulse with a spectrum. Basically we will get the shifted version of that, right? So 1 over ts n minus infinity to infinity m f minus n fs, or we can write 1 over ts as fs times n minus infinity to infinity m of f minus n fs. So let that sink in for a moment, and also side by side let me draw the spectrum of original analog message signal mt. Let's say this is the spectrum which we call mf. Let's say one-sided bandwidth is fm. That is what the spectrum of original message signal. So now see how things become easy. Now we have your sampled signal and we have found its spectrum, and the spectrum comes out to be what? Is nothing but the sum of shifted version of your original message spectrum. Let that sink in for a moment. This is your original message spectrum in analog domain. We sample it to facilitate the processing in the digital domain. Now we find the spectrum of the sampled signal, and it turns out to be a scaled version, scaled because you are multiplying with fs, and shifted, scaled and shifted version of by the way, it's a different shifted version because there are infinite number of n's possible. So basically you take the message spectrum, you shift by fs by 2fs up to infinite, like ideal case. You scale it with fs and you get the spectrum of sampled signal. So what does it turns out to be? So the spectrum of sampled signal is nothing by, let me write it down, infinite number of shifted okay, there is some internet issue. I see one of you mention. So is my voice breaking or the screen is not visible? What is exactly happening? Can you just clarify a bit more? Okay. Well, since I'm working from a desktop, so there is not a way to shift it. Is it okay now, or the voice is still breaking? Okay, let me do one thing. Let me close few tabs. Maybe that will help. Uh, okay, things should improve now because there are some tabs which I closed now. So I guess the system started hanging, but okay, it's okay, fine. Just don't hesitate to stop me again when the voice breaks. I'll then turn off the fan maybe. Okay, let's get back. So what do you see, that spectrum of sample signal is nothing but infinite number of shifted spectral copies of original spectrum MF. Now let us draw it, so when the actual things will come out. So let us draw it here. So this is the original message spectrum, and this is where I am drawing the spectrum of the sample signal. So for the sake of argument, let's say the amplitude here is 1. So in the spectrum, the sample signal, what we are going to see, let's talk about n is equal to 0. So I'll basically get MF scaled with Fs, right? So this amplitude is Fs now, and then I will have, this is Fm, this is minus Fm, then I will have, let's pick n is equal to 1, so another shifted version of M, that is shifted by Fs, the central frequency. So this is something, let's say here, this has its spectrum centered around Fs, this is Fs plus Fm, this is Fs minus Fm, and let's say another, let me draw it here, it's minus Fs, so it's minus Fs minus Fm, and here it is minus Fs plus Fm. Similarly, there are going to be infinite number of copies in both direction. So that is what my spectrum of sample signal is. This is M delta F. Now let us consider two scenario. One scenario, by the way, I have drawn here. See, I have made one assumption here that the Fs is sufficient so that there is this gap, right? These two are not overlapping. These are non-overlapping. But this need not be the case, right? Always, this is just one of the two scenarios. What is another scenario? So let me draw that also. But actually, you are going to see overlap. So I'm not drawing 3 copies here. I'll just draw 2. One is the one centered around 0. Another is just centered around Fs. This is Fs. This one here is Fs. this one here is 0, this one is fs minus fm, this one here is fm, and this one here fs minus fm. So now you can see there are overlap between the spectral copies of 2. So there are two scenarios possible, one which I draw earlier, which there is no overlap, so fs is kind of far, and here fs is bit close, so there is overlap between two copies. Now what is the condition for this scenario? You can see that your fs minus fm, this point need to be clearly greater than fm, this point, right? So 1 corresponds to this scenario, fs minus fm greater than equal to fm for non-overlapping. The second one you can see it's overlapping. And what is the condition here? Just the opposite, your fs minus m is less than equal to fm, fs minus m less than fm. So these are two conditions possible. Now what is happening here, if we have the first scenario, what we can do, we already have the spectrum where there is no overlap between spectral copies. What I will do, I'll just pass the sample signal to maybe call a filter like this, right? I mean, let's say I'll pick a filter like this, which is going to pass only this spectrum and which will stop this other spectrum at all. So essentially I'll get this spectrum. And what is this spectrum? This is just the scaled version of your original message spectrum. So scaling by like scalar term doesn't really matter, because it is not creating any distortion in the original message spectrum shape. So you can see that this will lead to successful recovery. So let me point it down. So what does that mean? That even if I am picking only few samples of the MT, if I choose a particular sampling period which will ensure this condition, and if I pass the sample signal through a low pass filter like this, I will get my original message spectrum. That means there is successful recovery of the original message signal. That is what I am calling no loss of information, because you are not losing any of the information, or another sense there is no distortion or no aliasing. And what is the condition for that? This one here. Whereas for the second case, when you are having this scenario, what will happen? Can you really separate? Can you get this original spectrum from here? You cannot, right? Because the moment I will try to pick this one, there is a part of this getting overlap. So it's impossible to recover the original message signal. So let me write it down. Impossible to recover MT. I mean, you can recover partly, there is no issue, but there is going to be distortion or aliasing. There is going to be distortion, or another way of saying is aliasing. So you can see it all comes down to this condition here. As long as you can meet this condition, everything is fine. There is going to be no distortion, no aliasing, no loss of information, and this is what known as Nyquist criteria. And how is that important? So what does it mean? Fs minus fm greater than equal to fm. So let me write it down by bringing this fm on the right hand side. So this means fs need to be greater than 2 fm. right? So fs is in your hand, right? Fs is your sampling frequency that basically tells you how many samples you should pick from the message signal. Now this condition is saying that as long as your sampling frequency is greater than equal to 2 times your message signal bandwidth, there is going to be no distortion or aliasing. So that is the key criteria. That is the central idea between the analog to digital conversion of a signal, that as long as you meet this criteria, you sample at a high rate enough, which is greater than equal to 2 times your maximum message signal bandwidth, you can recover your original MT without any distortion. There would not be any loss of information. The moment this criteria is violated, that is, you pick a sampling frequency that is less than 2 times your maximum message bandwidth, you will run into trouble, because then in frequency domain the spectrums are going to overlap, so there is no distortionless recovery is possible. So you are going to have some form of distortion or some form of loss of information. Now based on this criteria, let us just go back and answer the question here. So we have already pointed out what was the message signal. It's 250 hertz. So to ensure the no aliasing, the minimum sampling rate should be greater than equal to 2 times fm, right? That is greater than equal to 500 hertz. So the minimum should be 500 hertz. Let us move to our next question. So this is the next part, kind of you can consider the extension of the previous one. So it talks about a band limited signal, and let's assume we sample at a rate greater than the Nyquist rate. So now the question is, we are supposed to reconstruct the original signal from the samples via interpolation, and in this procedure what kind of pulse we are supposed to be using, that is the question. So this is, you can see, kind of extension of previous, in the sense when you talk about band limited signal, this is what I mean. This is a band limited signal. So you have done your first thing right, that is you sample at a rate greater than Nyquist rate, so there should be no distortion. Now the question is, you are trying to reconstruct the original signal from the samples via interpolation, and which pulse you are going to use for that. So let us draw the sampled signal spectrum again. So this band limited signal here, let's call it time domain representation MT, or frequency domain representation MF, and let's say it has the following shape. So it's spectrum of sampled band limited signal, given the condition that it is sampled at a rate greater than Nyquist rate, is going to look like following. 1 over f, sorry, the amplitude is fs. So you talked earlier that we have this following spectrum. Now I have to filter out this. So for that I am going to use a low pass filter. And what does the low pass filter does basically? So I am going to use a low pass filter. So this is minus fs over 2. I saw a hand raising, so is there any question? If you have any question, just feel free to ask. Okay. And this one here is fs over 2. So basically we have to pass the sampled signal through a low pass filter with cutoff frequency fs over 2. So that would kind of going to eliminate these two here and only let this part pass. And of course the amplitude, by the way, need to be 1 over fs, because you can see that original message spectrum is scaled by fs in the sampled version of the spectrum of the sampled version. So your low pass filter should have a cutoff frequency fs over 2 and amplitude 1 over fs, so that this cancels and basically you get this mf here. So let us denote this low pass filter impulse response as ht, which has a Fourier transform hf. So hf structure we know from here, which is given as this. 1 over fs by 2 minus fs by 2. So mathematically you can write hf as 1 over fs, and f mod of f less than equal to fs over 2 and 0 otherwise. This frequency, this Fourier transform we have also seen earlier. In the frequency domain, it's a rectangular pulse with one-sided bandwidth as fs. So what is going to be the time domain representation corresponding? Fourier transform. This is inverse Fourier transform. So in one domain, if we have a rectangular pulse, in another domain we are going to get a sinc pulse, sinc fs t. That is your low pass filter impulse response going to be. So this kind of answered the question here, but I would like to discuss few more things, how actually this reconstruction here takes place. So let us check that. Reconstruction procedure. So you have your sampled signal, m delta t here, that you are going to pass through this low pass filter with impulse response ht. You are going to get the original message signal mt. So that means your here goes in m delta t, here comes out mt, and your response is ht here. So basically it's mt, the original message signal, is supposed to be the convolution of sampled signal with the low pass filter impulse response. Now what is the expression of sampled signal here? It's a time domain representation. We have seen it is n runs from minus infinity to infinity, m values at these particular locations times the impulse strength. And ht, we have just found it to be a sinc pulse. Now when I convolve these two, what I am going to get is by the way, remember mnts is a scalar, it's a scalar, it's not a variable of it's not a function of t, because we have already fixed the sampling period, so it basically just become a scalar term, amplitude, that's all. T minus nTs convolve with sinc ft. So you can keep the scalar part mts as it is. Now the thing is happening is the convolution between this impulse train and this sinc function here. So we'll get sinc, it should be fs here, fs times t minus nts. N minus infinity to infinity m nts sinc fs t minus n fs ts, and fs is just nothing but 1 over ts, so that would become n minus infinity to infinity m nts sinc fst minus n. And what is this basically? These are shifted copies of sinc function. And remember, this is going to be your m hat t. Let us call it m hat, and let me not write it as original message signal. I should have write it as reconstructed message signal m hat t. That should ideally be equal to mt, but of course there is no guarantee. So the reconstructed message signal has this following expression. We have these scalar amplitudes mnts, and you have these shifted copies of the sinc function. So it's like the shifted sinc pulses are scaled by the message function values at these certain intervals. These are basically the sample values. So let me write it down. Insert another slide here. Reconstructed message signal m hat t is sum of shifted sinc pulses that are scaled by sample values m n t s. Let me give a graphical representation of the same. By the way, this, when I say that sum of shifted sinc pulses, this is nothing but sinc interpolation. So you all know that sync pulse structure. Let us draw one. This is corresponds to the sync pulse here, n as 0 and its maximum value is scaled as m0. So this is here m0. So this here, the shifted sync pulse corresponds to Ts. Ts corresponds to 0. This has amplitude m Ts. Similarly, we will have multiple sync pulses here on both sides, and when you sum them up, basically you interpolate it, you get back your original message signal. That's the idea of the reconstruction. So in case, in ideal scenario, if we have done everything right, like you have sampled the signal at greater than the Nyquist rate, and you are using these ideal pulses for sampling, then in ideal scenario, your reconstructed message signal should exactly match with your original signal MT. So the answer here is the sync pulse. Now let us move to our next question. We are given a message signal cos 5000 pi t, and it is said that it is sampled using an impulse train with sampling frequency 8 kilohertz, and then we pass it through a low pass filter which have a cutoff frequency of 11 kilohertz. So the question is, what are the frequencies of sinusoid that is going to be present at the output of the low pass filter? So let us look at that. So we have MT here, which is just a moment. We have MT as cos 5000 pi t. So you can write it in terms of complex sinusoid as 1 over 2 e to the power minus j 5000 pi t plus e to the power j 5000 pi t. So we have already seen that if you have complex sinusoid in time domain, that is equivalent to shifted impulses in frequency domain. So this MT here, if we call its Fourier transform MF or frequency domain spectrum MF, it has following structure. There are going to be just two impulses at 2.5 kilohertz. That's all. So basically it's Fourier transform you can write as 1 over 2 del f minus 2500 plus del f plus 2500. Now the impulse train has sampling frequency of 8 kilohertz. So basically sample at 8 kilohertz. So you have seen that let us write down the expression of spectrum of sampled signal is given as m delta f as fs times the shifted spectral copies of your original spectrum minus n fs. So let us just forget this scalar fs for a moment, because that is not going to play any role apart from scaling the amplitude. So this we can write as mf at center, then the delayed version f minus fs plus m f minus 2fs, similar higher delay version, and then comes the advanced version f plus fs f plus 2fs, similarly higher advanced versions. Now put these mf values here. So let us consider this 5 terms that we pick, m of f plus 2fs plus m of f plus fs, then comes m of f, then m of f minus fs plus m of f minus 2fs. So there are two information is that mf is given as, again I am forgetting the scaling factor 1 over 2, just pick these two, f minus 2.5 k, k represent for kilohertz, and del f plus 2.5 k. So for mf, let me write in the center, it's del f minus 2.5 k plus del f plus 2.5 k What about this? This is divided by fs, so that means del f minus fs is 8, so it's 10.5k plus del f minus this is 8 minus 2.5, so 5.5k. So this 2 corresponds to this one here. This one here you can see that f minus 2 fs, so that means it's divided by 16 k, because fs is 8 kilohertz. Let me write it down here. Fs is 8 kilohertz, so that is well beyond the range of let me write it down for this also. Del f minus 16 plus 2.5, that is 18.5k plus del f minus 13.5k. Similarly on this side we'll have f plus fs, so plus 8 will be there, so del f plus 10.5k plus del f plus 5.5k. Similarly on this side we'll have del f plus 18.5k plus del f plus 13.5k. Now what does the question say here? It says your low pass filter has a cutoff frequency of 11 kilohertz. So who are going to fall within 11 kilohertz range are these people. A low pass filter with cutoff frequency 11 kilohertz is going to pass all of them. Because this corresponds to, let us draw that entire spectrum and then we'll so we have spectrum at 2.5, we have spectrum at 2.5, we have spectrum at 5.5, we have spectrum at 10.5. Similarly here also we have at minus 2.5, minus 5.5 and minus 10.5. We have other spectrum also at 13.5 and 18.5. So let me just draw those. So we'll have 2.5, 5.5, 10.5, 13.5 and 18.5. Similarly here minus 2.5, minus 5.5, minus 10.5, minus 13.5, minus 18.5. And low pass filter is only going to let pass this part. Outside this cancels everything. So you are going to see the frequency component 2.5 here, 5.5 and 10.5. Let us go and check. So the sinusoids present here corresponds to this second one. Let us move to your next question. So we have the message signal now, which has a structure of sync cube, and we are supposed to find the minimum sampling rate that is required to avoid the aliasing for this particular signal. So we know that first of all, let's assume we are talking about sync function only, not sync cube. So sync 20 pi t, and we know its frequency domain representation or the Fourier transform is going to be a rectangular pulse, right? Rectangular pulse with the one-sided bandwidth 20 pi. We have minus 20 pi. Let's call it PF. With bandwidth 20 pi. So by the way, when I'll have a sync cube here of any function, that is going to have part sine cube also. It will be sync sine cube by x cube, but I am not interested in the x part, I am interested in the sine part. So the sync, okay, let's see it from other point of view. This sync cube 20 pi t, we can write it as sync 20 pi t multiplication with another and the final third one. So multiplication in time domain, what is going to do in frequency domain is going to be convolution. So you'll have PF, oh sorry, this is one thing I made this mistake, it's one sided is 10 pi not 20 pi, the overall base is 20 pi, sorry about that, it should be 10 pi. So bandwidth is also not 20 pi, it's 10 pi only. So we are going to have convolution 2 times. This is because your multiplication in time domain is going to have convolution in frequency domain. So here we have convolution of rectangular pulse with itself 2 times. So what happens when you convolve spectrum, any finite spectrum with a version of itself, it basically expands, right? Like, let me write it down here. Spectrum convolution with itself n times bandwidth increases also n times. So So if I convolve a finite spectrum with itself n times, I will see a bandwidth increment of n times. So you can see for sync pulse, uh, the rectangular pulse here in the frequency domain has bandwidth, one-sided bandwidth of 10 pi. So for the this one here, sync cube 20 pi t, the frequency domain representation, I am not worried about the shape of the spectrum, but I am worried about the uh, bandwidth of the spectrum. And what is the bandwidth going to be? The bandwidth is going to be 30 pi here, because we are convolving it two times. Had it been one time convolution, it would be 20 pi, two times is 30 pi. So 1 sided bandwidth 30 pi. Let me just clarify it. Bandwidth increases n times. So this signal here, sync cube 20 pi t, has a one-sided bandwidth of 30 pi. And for a signal having bandwidth 30 pi, what is the minimum sampling rate required to avoid aliasing? We know already that fs need to be greater than 2 fm, and fm here is 30 pi, so your sampling rate should be 60 pi hertz. So here we are supposed to have a message signal with maximum frequency fm. So what is the minimum sampling rate required to avoid distortion? That's quite trivial, we have already answered this. This is Nyquist rate. Okay, this one here is an interesting question. So you are given a parallel resonant LC circuit with a certain inductance and capacitance value, where capacitance, by the way, varies with time. So, and it actually depends on the message signal, so we can say that the capacitance is modulated by the message signal. And it is given also a property that the maximum value of message signal is well beyond 1, it's like far less. So we are supposed to find the approximate carrier frequency of the resulting frequency modulated signal xct. So the question looks a bit tricky, but actually the idea is you need to find basically the resonance frequency of the parallel LC circuit, that's all. So what is the resonant frequency expression of parallel LC circuit? Resonant frequency fc is given as 1 over 2 pi square root of lc. And by the way, we are given the property that maximum value of mt is less than equal to 1. Basically we have to compute the resonant frequency of this LC circuit. This is the carrier frequency of the signal. So basically the job of the parallel resonant circuit here is to generate the frequency modulated signal, and the resonant frequency of this circuit becomes the carrier frequency. So that's pretty much it. So let us just put these values here. So 1 over 2 pi square root L is given as 1 image, so that is 10 to the power minus 3, and C is given as 50 microfarad, that is 50 into 10 to the power minus 6 minus 10 to the power minus 7 mt. Okay. So let's consider this. What is the multiply here? This is 10 to the power minus 6 and minus 3, 10 to the power minus 9, 15 10 to the power minus 9. That is 5 into 10 to the power minus 8. So let me take that common. 5 into 10 to the power minus 8. This make the first element 1, and what about the second element here? So this one here is 10 to the power minus 8 is given common, so inside should be 10, and what else? Inside should be 10, and 5 is also taken common. Okay, 10 to the power minus 3 is there already. Okay, so this multiplication become 10 to the power minus 10, and so if 10 to the power minus 8 is taken outside, inside is 10 to the power minus 2 at 10 to the power minus 2. Okay, and 5 is taken, so it's inside it should be 1 over 5 into 10 to the power 2 times mt. Did I do correct? 1 over 10 to the power minus 2. Yeah, that's correct only. So here you will have 10 to the power minus 8 comes out to be 10 to the power 4 comes above. Below you will have 2 pi square root of 5, and you will have 1 minus 1 over 500 times mt, mt to the power half. So by the way, we have seen that maximum value of mt is far below 1, and by the way that is also multiplied by 1 over 500. So this term is pretty small compared to 1, right? So you can make this approximation which says that 1 minus x whole to the power minus half can be approximated as 1 plus 1 over 2x, given your x is much less than 1, so that's criteria is fulfilled here. So you can write it like this: 10 to the power 4 by 2 pi square root of 5, 1 plus 1 over 500 times 1 over 2, that is 10 to the power minus 3 mt. Oh, sorry, it should come above, because it was denominator, so if it goes above it becomes 1 minus 1 over 500 mt times minus half, that is what is being taken here. So I'll have this 1 plus 10 to the power minus 3 mt. Now you can see that maximum value of mt is quite less than 1, and it's multiplied with also 10 to the power minus 3, so this term here approximately goes to 0. So essentially you are left with 10 to the power 4 divided by 2 pi square root of 5. This is supposed to be our carrier frequency. Let's just calculate it. So this becomes 5000 by pi square root of 5. Let me just check what is the result is. Five thousand divided by pi here divided by 5 square root 711.76 is 711.76 hertz. So this is going to be the approximate carrier frequency for the parallel RC circuit which generate the frequency modulated signal XCT. Second one is the correct answer. Okay, let us look at another similar question we have seen earlier. So MT now is cos 500 pi t. We know that can be written as 1 over 2 e to the power j 500 minus pi t plus e to the power j 500 pi t. So the Fourier transform is going to be 1 over 2 del f minus 250 plus del f plus 250. Now this is the mf here. Now we have our sampling frequency 400 hertz. Sampling frequency 400 hertz. So sampled signal spectrum is given as m delta f as fs times m f minus n fs. Let me ignore the amplitude part fs here. So let us focus on the shifted version of mfs. So we have done earlier. We will take three values m f plus n fs plus m f and m f minus fs. There are other values on both sides, but they don't matter much because they don't interfere since we are passing it through this low pass filter of 500 hertz. So what are you going to get? Now mf corresponds to del f minus 250 plus del f plus 250. F minus fs corresponds to del f minus 650 plus del f plus 150, and here also similarly del f minus 150 del f plus 650. I think fs minus, okay, it's correct only. So what are the frequency components when I pass it through a cutoff filter of 500? So only these ones are going to pass, these three here and this. since this falls outside the 500 hertz, these are not going to pass. So there are two components you can see, one is 150 hertz, another is 250 hertz. So first one is the answer. So we are given our signal MT as 50 sine 25 pi t by 25 pi t. It basically makes it a sinc function. So if I take the Fourier transform, we will have a rectangular pulse with bandwidth 25 over 2, right? That is 12.5 hertz, because this 25 corresponds to the entire base. So since it's centered around 0, we are picking the one-sided bandwidth, that is 12.5 hertz. So the minimum sampling rate Fs, which is 2 times this one-sided bandwidth, this is Fm, is given as 25 hertz. The first one is the answer. So we are given a message signal MT, which is band limited to FM. So this is again same as Nyquist criteria, so nothing much. It's 2 FM. Last one is that we are given a signal with the spectrum MF, which is sampled with an ideal impulse of sampling frequency Fs. What is the spectrum of resulting sampled signal? So we have already seen that the sampled signal spectrum M delta F is given as Fs time infinite number of shifted spectral copies of your original spectrum. So the second one matches. The second one is the correct answer. So this is pretty much all I have to discuss for this session. If you have any questions, feel free to ask. So you can ask any question regarding today's session. If there aren't any, we can conclude here, and we'll meet again on next Saturday. Thank you everyone. Okay, it seems there aren't any questions, so I'm concluding this session. Thank you, everyone. Thank you. Thank you for attending this session. Bye.